I'm Steve Brusatte. I'm a paleontologist. I dig up dinosaurs. I teach at the University of Edinburgh. I advise on films like the Jurassic World films, and I write pop science books like The Rise and Fall of the Dinosaurs and the new one called The Story of Birds.
Chapter 1: The Rise and Fall of Dinosaurs.
The story of dinosaurs actually begins in tragedy. Dinosaurs emerged from the worst mass extinction in the history of life, the closest life has ever come to completely dying out. And this happened about 250 million years ago at the end of what we call the Permian period of Earth history. And this was the time where there was the supercontinent, Pangaea. All of the land was gathered together as this one enormous landmass stretching from the North Pole to the South Pole. And it was a landmass that was ruled by a lot of early relatives and cousins and ancestors of us, distant mammal ancestors. But then, in what is now Siberia, these enormous volcanoes started to erupt about 250 million years ago. And these are not volcanoes like those that we know today. It's hard to even envision what these were like. These weren't the Hawaiian volcanoes or Mount Pinatubo blowing its top one day. No. These were enormous fissures in the earth. It's like the earth was slashed with a giant machete and it bled lava for millions of years. And as that lava came up through those cracks in the earth, it burnt its way through all the rocks. And that released unholy amounts of carbon dioxide and methane and other greenhouse gases that warmed the atmosphere, led to runaway global warming, and that caused an extinction. And not just any extinction, but the granddaddy of all mass extinctions. 90 or 95% of all species died out. But there were a few plucky survivors. And among those survivors were some small little reptiles that had long arms and legs, that could move fast, that were agile, that were smart. And it's in those reptiles that we find the roots of the dinosaur family tree. Some of the fieldwork that I've done with friends and colleagues of mine in Europe has identified some of the first very tantalizing clues of those dinosaur ancestors living soon after that terrible extinction at the end of the Permian. And these are in many ways very meager clues because they are not nice, beautiful, complete skeletons like you might see in a museum. But they are tiny little footprints and handprints, just a few centimeters long. And we find them in Poland. And these little footprints, they were made about 250 million years ago. They were made by these little reptiles that we call dinosauromorphs, which were no bigger than a cat, than a pet cat that we might have. I could hold one of these in my arms. From those humble ancestors came the true dinosaurs. And the first true dinosaurs, we find their fossils about 230 million years ago in the Triassic period. And really, they're just distinguished by a few changes in the pelvis and the backbone that allowed them to walk more upright and move more quickly. And these very first dinosaurs, they split into the three major groups of dinosaurs. And these were the theropods, those are the meat-eating dinosaurs, the ones that would eventually become T-Rexes and velociraptors and birds. Then secondly, there's the sauropods and their close relatives. Those are the long-necked dinosaurs, the brontosauruses and platycuses and brachiosauruses. And then the third group is the ornithischian dinosaurs. And this is a whole variety of mostly plant-eating dinosaurs that had beaks and that could chew their food really well, like Triceratops. The ones with plates on their backs, like Stegosaurus. The duck-billed dinosaurs, the armored dinosaurs, the ones with the dome heads that headbutted each other. Those are all ornithischian dinosaurs. So, as you can see, there's this great diversity of dinosaurs that was starting to establish itself in the Triassic period on the supercontinent of Pangaea. But this was not an easy thing for these first dinosaurs to do because they had a lot of competition from the animals that were living with them, but they also were kept in check by the weather, by the climate. When it comes to the physical environment, Pangaea was not an easy place to live, not at all. This enormous supercontinent was so big that much of the interior was thousands of miles from the oceans, from the shoreline. So there were vast deserts covering much of the supercontinent. But the shorelines weren't really that much more hospitable because the shorelines were battered by storms, by what geologists call mega monsoons, which sounds very hyperbolic, but it is what they were. They were supersized monsoon systems. So that's the sort of weather and climate and environment that these early dinosaurs would have had to face. But also, they were in this battle of survival and this battle of evolution with other groups that had also survived that terrible extinction at the end of the Permian. And some of those groups were amphibians. The rivers and the lakes of Pangaea were ruled by salamanders the size of cars, with enormous heads with thousands of teeth. There were crocodiles and their relatives living all across Pangaea, and some of them were meat eaters, some of them were plant eaters. Some of them had beaks, like a turtle. Some of them had sails on their back. Some of them walk only on their hind legs. There was an enormous menagerie of fossil crocs, and these were the competitors of the very first dinosaurs. And there were more of these crocs, and they lived in more places, and they were more diverse in terms of their diets and their habits and the way that they lived. And so really the Triassic period, for many tens of millions of years, yes, dinosaurs were there. Yes, dinosaurs were diversifying, but they were really second-rate characters, B-list actors in this Pangaean drama, a drama that was headlined by the crocs and the giant salamanders. And it would have seemed like those animals would have kept going, kept evolving, kept thriving, kept dominating. But something happened. Something changed that story. Back at the end of the Triassic period, once again, another mass extinction. And this was caused by the breakup of the supercontinent. And you can see the legacy of that. South America and Africa look like two puzzle pieces that fit together because they once were together. And then Pangaea broke apart. And the earth bled lava. And it was a time of major volcanic eruptions all across what is now the Atlantic seaboard. And once again, as that lava came up, it burnt through the earth. It released a lot of carbon dioxide. It led to global warming. It led to an extinction. Not quite as bad as that one at the end of the Permian, about 50 million years earlier, but still one of the worst sudden moments of death in Earth history. And that extinction decimated the crocodiles. Almost all of them went extinct. Only a few species survived, the ancestors that led to the crocodiles of today. Same with those giant salamanders. Most of those died out. But the dinosaurs, they just sailed right on through that extinction. They were the great survivors of that extinction. They were the success stories. And because they passed through that extinction, they had the opportunity to diversify in this largely empty world in the next interval of time, the Jurassic period. Now, I wish I could tell you exactly why dinosaurs survived. But the truth is, I don't know the answer. Nobody really knows the answer. The answer must be out there. There's lots of different ideas that have been proposed. Maybe the dinosaurs could move faster. Maybe they were more intelligent. Maybe they had feathers to insulate their bodies against the whims of climate change. Many other ideas, but it's really hard to know. And so about 200 million years ago, the extinction happens, the volcanoes erupt, global warming causes a lot of species to die, dinosaurs make it through. Now, the Triassic period transitions into the Jurassic period. And there's a reason why the book, the film, is Jurassic Park, or the new ones that I work on are Jurassic World. And that's because it's in the Jurassic that dinosaurs truly become the stupendous, spectacular, sublime creatures that we all know and love. Giant meat eaters the size of buses, long-necked dinosaurs that got as big as Boeing 737 airplanes, the ones with horns and spikes and duckbills and dome heads and armor and all of those fantastic things that make dinosaurs so engaging. This is happening in the Jurassic period. And dinosaurs are diversifying so much in the Jurassic period, really for two reasons. First of all, they survived that extinction that killed off a lot of their competitors. So the playing field was largely empty, and dinosaurs had an opportunity. They were pioneers. They could go out and make their own destiny in this new evolutionary landscape. But also, Pangea is now breaking apart. What was once a single unified landmass is now fracturing into many bits and pieces, and the dinosaurs were along for the ride. And as these different continents budded off, broke off, spun off of Pangea, the dinosaurs adapted and changed as their environments changed. And from that, by the end of the Jurassic period, we had a whole stunning array of dinosaurs living all over the world, different species in different places, including some of the most famous dinosaurs of all, like Brontosaurus, Brachiosaurus, Stegosaurus, Allosaurus, living in the American West. And today we find their fossils in places like Colorado and Wyoming and Montana, Utah, and the Dakotas. These are some of the richest fossil sites in the world, and it's Jurassic dinosaurs that we can find there. About 103 million years ago, the Jurassic transitions into the Cretaceous. And unlike many of the other transitions in Earth history between one period and another, this one is not marked by some great extinction or some spasm of volcanism or the impact of an asteroid. It really is just a line geologists use to divide a long time frame. But you have dinosaurs continuing to adapt and evolve as the continents move around. Now, where we really start to see a change is a little bit later in the Cretaceous, in the middle part of the Cretaceous. But here things get a little bit frustrating again, because the fossil record largely goes silent. We know things are changing because we can see that in the early Cretaceous, there are certain groups of dinosaurs that are dominant and diverse. You have things like the Spinosaurs with the sails on their backs and the long snouts that ate fish and swam around in the shallow water. You had big Carcharodontosaur predators. Then later on in the Cretaceous, they're gone or mostly gone, and you have Tyrannosaurs and other major groups. But best we can tell from the rocks that we have and the fossils that we have, and especially the clues of the chemistry of the rocks, which can tell us a lot about temperature and precipitation and sea level and climate, it seems like there was a period of climate change, a period, again, of global warming, a period where sea levels were moving around. And out of that came new types of dinosaurs. And the dinosaurs that were able to survive that interval of climate change in the Middle Cretaceous, they were the ones that then had the opportunity to take over in the Late Cretaceous. But still, again, this is largely a mystery. By the latest Cretaceous, and I'm talking between about 80 million years ago and about 66 million years ago, by that time, the continents had moved around so much that Pangea was a distant memory, and a map of the world would have looked pretty similar to the world today. There were small differences. Sea level was much higher. There were no ice caps at the poles. India was an island in the middle of the ocean racing northwards to collide with Asia. But by and large, if you looked at that map, it would look similar to us. And on those different land masses lived different dinosaurs. The ones in North America were quite distinct from the ones in South America and the ones in Africa. And where we really see that is with the top predators. The latest Cretaceous, this was the kingdom of T-Rex, but only in North America. There were other close tyrannosaur relatives that topped the food chain in Asia, but south of the equator, in South America, in Africa, it was totally different dinosaurs called abelisaurs, much more primitive dinosaurs that were the top predator. In Europe wasn't really even a continent. It was just a bunch of islands poking out of the sea. There were not many big dinosaurs there at all. There were a lot of smaller dinosaurs living on those islands, and it was little raptor dinosaurs that were the top dinosaur predators, and other groups of animals like the pterodactyls, which were not dinosaurs. These were another group of reptiles that could fly, but they were not dinosaurs. They were the biggest predators in many parts of Europe, and it's all because of the geography, because different continents, different land masses had different climate, different weather patterns, different environments, and that bred this richness of dinosaur diversity. And it really does seem that in the latest Cretaceous, this was the apex of dinosaur diversity. the time when they were thriving most, when there were most species, the largest number of species, different species living in different places, a world in which dinosaurs were firmly in control, even though it wouldn't last a whole lot longer. If you woke up on the last day of the Cretaceous period 66 million years ago, you would have woken up to a world thrown into turmoil. This was an asteroid. And not just any asteroid, the biggest asteroid that was sniffing around our part of the solar system over the last 500 million years. It was about 6 miles wide, about 10 kilometers wide or so. So, a pretty sizable rock. And it smashed into what is now the Yucatan Peninsula of Mexico in a split second. And I mean that in a literal sense. In a split second, it detonated with more energy than a billion nuclear bombs put together. And it punched a hole in the face of the Earth over 100 miles wide, a crater that we can still see in parts of Mexico today. It's largely covered by the Gulf of Mexico, but parts of it are visible on land around Cancun. That asteroid, it triggered earthquakes, it triggered tsunamis, it triggered volcanoes going into overdrive, hurricane-force winds. The atmosphere got so hot from all of that energy that forests spontaneously combusted. There were wildfires all over the world. And those were the things that just happened in the first few minutes and hours and days after the asteroid hit. The real killer, though, was what happened over the next few weeks and months and years, and that is that the soot from those fires, the dust and the dirt and the grime from the collision of asteroid hitting Earth, all that stuff went up into the atmosphere. And there's currents in the atmosphere just like in the ocean. And that stuff spread all around the world, and it cloaked the Earth in darkness. It was a nuclear winter, a global winter that lasted for maybe a few years, maybe up to a decade or so. The Earth went dark and cold and silent. Plants did not have sunlight to photosynthesize to make their own food. So over a quite short period of time, plants died, forests collapsed. Plant-eating animals had very little to eat. They died. Then the meat-eaters. Ecosystems collapsed like houses of cards. And this led to a mass extinction. This is the most recent mass extinction to today, so it's the last one that happened. And 3 out of every 4 species died. So if you were living that morning before the asteroid hit, your entire species had a 25% chance of making it through. Everything bigger than a husky dog that lived on land died out. It was probably just too hard to get food, too hard to hide if you were big. But even a lot of smaller animals died as well. All of the dinosaurs, despite all of their previous successes, all of their millions of years of dominance, they died. Only one weird type of small, feisty, plucky, quite sophisticated dinosaur made it through. These were the dinosaurs with feathers and wings that could flap those wings and fly. These were the birds, the only dinosaurs that have survived to the present day. And many other animals died as well. The pterodactyls died. All the reptiles living in the oceans died. The ammonites, those beautiful coiled shells, they died in the ocean. But, of course, some things survived. And among the survivors, in addition to birds, were some tiny, furry, smart, feisty little creatures that could dig burrows and hide away and survive by their intelligence and by their endurance. And these were our mammal ancestors. We had ancestors that stared down that asteroid. And it's because they were able to endure this worst moment of Earth history. Because of that, that is why we are here today.
Chapter 2. T-Rex, the king of dinosaurs.
With the fossil record, we can trace evolution over time. That's one of the main reasons why paleontologists like me study fossils. We want to understand evolution. And what we see with dinosaurs, when we have a good enough fossil record, we can trace a single lineage over tens or even hundreds of millions of years. And to give an example of that, I'll just turn to my favorite dinosaur, the most famous dinosaur. Some might say the most overrated dinosaur, but I think it deserves all the accolades that it gets. That, of course, is T-Rex, the tyrant lizard king, the king of the dinosaurs. And it was the top predator in North America at the very last stage of the dinosaurs at the end of the Cretaceous. But it wasn't always that way. T-Rex came from a long line of ancestors that changed and adapted and endured and survived. And believe it or not, the fossils show that the Tyrannosaur family goes back more than 100 million years before T-Rex. T-Rex was the crowning achievement of a long period of evolution. And for most of that time, tyrannosaurs were not very special. They just simply weren't. For most of that time, tyrannosaurs were basically my size. Now, the very first tyrannosaurs we see are from the middle part of the Jurassic period. We have a few very scrappy, very tantalizing fossils, a little bit of a foot, one tailbone, a few teeth that my crew has found on the Isle of Skye in Scotland, where we do a lot of our fieldwork. But there are better fossils of that age from China. And these very first tyrannosaurs, like Guanlong from China, these lived about 165 to 170 million years ago. They were the size of humans, literally the size of humans. And in fact, some of them were even smaller. Some of the other early tyrannosaurs were just the size of lapdogs. They were not top predators. They were second or third tier predators in the food chain, living underfoot of giant allosaurs and spinosaurs and other terrifying dinosaurs from other groups. And they were very good, it seems, at that role, at being smaller predators. Now, over the course of the Jurassic, tyrannosaurs stayed pretty small. They made it into the Cretaceous. They got a little bit bigger. Some of them got to be about the size of horses. A few random species here and there kind of supersized themselves in their own local environment. But by and large, they remained small predators until this middle Cretaceous turnover in dinosaurs, this time of climate change that we don't know much about. But we know that it wiped away many of the incumbent top predators, the spinosaurs and the allosaurs and the carcharodontosaurs. And so with those animals out of the picture, now a job was open at the top of the food chain. And in North America and in Asia, tyrannosaurs filled that job. And they did so by supersizing their bodies and becoming the size of buses. T-Rex was the size of a city bus. But what is incredible about T-Rex to me isn't just that it was so big, it's that it was also a very smart animal. And as is often the case with celebrities, there are a lot of misconceptions about T-Rex. And frankly, a lot of those do come from the first Jurassic Park film. And not to rip on the film, I love that film. That film was one of the things that inspired me to become a paleontologist. And of course, now I work with the franchise consulting on the newer Jurassic World films. And in fact, we've corrected some of these misconceptions in the latest film in Jurassic World Rebirth. But to run through some of these, in the first Jurassic Park, we see the T-Rex chasing down the Jeep that a lot of the characters are in. And this Jeep is probably in third gear. This thing is moving probably at least, 30 miles an hour or so. In reality, T-Rex probably could not move that fast. We don't know for sure, but paleontologists have built computer models and have done simulations. And it just seems that an animal of that size, of that bulk, of that stature, simply could not move at that speed. It could probably top out at about 10, maybe 15 miles an hour. Still quite fast, but not fast enough to run down a Jeep at that speed. But there are other things in the films that don't give T-Rex enough credit. So yeah, the film makes T-Rex look faster than it was, but the films also make T-Rex, frankly, look a bit dumber than it would have been in real life, especially when it comes to its intelligence and its senses. We see in the film this storyline that if you stand still, the T-Rex cannot sense you. Now, in reality, you would be bait because it had a pretty big brain for a reptilian creature of its body size. Its brain had big olfactory bulbs that controlled a very powerful sense of smell, big optic lobes that powered keen vision, an ear with a really long cochlea, And we know from modern animals, the longer the cochlea, the greater range of sounds you can hear. So T-Rex was a smart animal. And we can tell from the fossils that some of the ancestors of T-Rex, while they were still small, while they were still the size of humans and horses, it was then that they were developing these larger brains and keener senses. So it seems that being smart may have helped tyrannosaurs endure this Middle Cretaceous extinction. Now, how did it hunt, though? That's a question that a lot of paleontologists have wrestled with. And these are difficult questions to answer, frankly. But there is some evidence that tyrannosaurs were pack hunters. And that is different than how they're often depicted in films as these solitary murderers. Now, the evidence that we have is that there's a few species of tyrannosaurs that have been found in bone beds. And basically, bone beds, that's just the term that we use as paleontologists for a mass graveyard. And these bone beds, they have only bones of the same species of tyrannosaur, of many different individuals, from juveniles up to adults. So if you preserve a whole bunch of individuals together in a mass grave, that is a good sign they must have been living together. And if they were living together, maybe they were hunting together. The thing about T-Rex that always throws me, because it's an incredible animal, I mean, the size of a bus, head the size of a bathtub, 50 banana-sized teeth in his mouth. It could crush the bones of its prey. The ultimate predator from Earth history. But its arms were the size of my arms. And my arms are not that big. So how could such an incredible, sublime animal have such pathetic arms? It is a riddle that goes back to the discovery of T-Rex in the early 1900s. And we don't honestly know for sure why the arms were so small, but we have a pretty good idea. And that comes from a few things. First of all, we can see that over the course of tyrannosaur evolution, tyrannosaurs started small. First tyrannosaurs were the size of people, the size of dogs. They had longer arms and smaller heads. But over time, as their bodies got bigger, the heads got bigger and bigger, the arms got shorter and shorter. So it definitely seems like there was a trade-off, and the head was taking on most of the jobs that the arms once did in terms of grabbing and processing food. So something like T-Rex really was like a giant land shark. It would have led with its head, done most of the work with its head. But the arms were still there, and that's the interesting thing, because if a structure is totally useless, evolution will usually just get rid of it or make it so tiny that you can barely see it. Like the hind legs of whales. You know, whales evolved from mammals that lived on land. They had hind legs. They went into the water. They lost those hind legs. So the fact that T-Rex still has arms, that means something. The other thing that means something is, yeah, the arms are the size of my arms in terms of how long they were, which is weird. You know, this is a bus-sized animal with arms the size of my arms. Very strange, but those arms of T-Rex were very muscular. Much, much, much more muscular than my arms. And we can tell because muscles leave scars on the bones, and those scars are huge on the T-Rex arm bones. Now, the muscles that were really big on the T-Rex arms were the ones that would have brought them closer to the body, like this. So that motion must have been something that they were doing quite regularly that was important to them. And we can speculate. Maybe they were holding on to each other when they were mating. Maybe when they were feeding with their mouths, they were bracing themselves with their arms. Or maybe if they were two T-Rexes that were fighting over a kill, they could grapple with their arms a little bit. There's a lot of different possibilities, but the fact that the arms are there and the arms are muscular means they must have been doing something. They must have been part of the repertoire of T-Rex behavior. When we look at the depiction of dinosaurs in a lot of films, especially older films and older books, older television programs, but even some that are put out today, there is one glaring issue, one glaring piece of just total unreality. And that is that many dinosaurs were not covered in scales. They wouldn't have been green or brown like some big reptile. In fact, many dinosaurs had feathers. Many dinosaurs had feathers all over their bodies. Even some dinosaurs had wings on their arms. Velociraptors had wings on their arms. We know this because we know it directly from fossils, from real fossils. Now, these fossils were first found in the mid-90s. One is a little dog-sized tyrannosaur called D-Long, a primitive one. The other one is called Eutyrannus, and it's big. It's about 30 feet or about 8 or 9 meters long. It weighed over a ton. And that means that T-Rex itself probably had some kind of feather. We don't know for sure. T-Rex is from North America. It has never been found fossilized in those conditions that allow feathers to be preserved, so we don't know for sure, but we know its ancestors must have had feathers. Now, I know that is a controversial thing, kind of a weird thing. I think for some people, I get this. I get messages. People send me emails decrying this. Oh, you've taken away this idea of T-Rex I had from childhood as this giant primeval reptilian monster, and it's no longer scary, and you've made it this fluffy, feathery thing. No. First of all, we got to deal with the fossils we have. So if it had feathers, it had feathers. Your feelings don't matter, sorry. But I think a big old feathery T-Rex is even more terrifying, even more frightening than a T-Rex without feathers. But at the end of the day, we got to deal with the fossils that we have, and it's undeniable that at least some tyrannosaurs had feathers all over their bodies. More dinosaurs now are being found than ever before. And believe it or not, there's a new species being found about once a week on average. So about 50 new species every year. Now, you add them all up, and we know of maybe about 2,000 species of dinosaurs, which sounds like a lot. It is a lot, but dinosaurs lived for well over 150 million years. They actually still live on today in the guise of birds, and there are over 10,000 species of birds just alive today. So really, there were probably millions of species of dinosaurs that once lived. We've only found a tiny fraction of those dinosaurs. It means there are a whole lot more dinosaurs out there to be found.
Chapter 3: The Rise and Reign of Mammals.
I mostly studied dinosaurs during my career as a paleontologist. It certainly was dinosaurs like T-Rex that got me enthused about science as a teenager. But the more I've studied dinosaurs, the more I've also expanded out to study other groups, and I've become particularly enamored with mammals. And really, there's probably two reasons for this. First of all, I am a mammal. We are mammals. So if we want to understand our own history, our own origin story, we need to understand mammal evolution. But also, really the dinosaur story and the mammal story, it's the same story. That asteroid comes down out of nowhere, ends the age of dinosaurs, but some mammals make it through and forge a new world. And so the more I studied that extinction, the more I, of course, became interested in, well, how did the Earth recover? What happened after that extinction? And the story there is that the age of dinosaurs gives way to the age of mammals, and that's what we've been in for the last 66 million years. We are mammals, and we know we are mammals, not just from our DNA that proves it, but more broadly because there are many features of our own bodies, our own behaviors that are classic mammal hallmarks. So we have hair. Some of us have more hair than others, but we have hair, and that's a mammal thing. We have molar teeth and premolar teeth and incisors and canines, the different teeth in our mouths that are used for grasping and shearing and crushing. Classic mammal features. We feed our babies milk, a classic thing that mammals do. And then even more broadly, things that maybe we don't necessarily appreciate because there may be more nuanced things that only an anatomist or a paleontologist might think about. But we, of course, have big brains. We have keen senses of smell. Those are classic mammal things. We have very, very, very good sense of hearing. That's a mammal thing. We have a single lower jawbone. That's a mammal thing. That bears teeth, but one set of baby teeth, one set of adult teeth. That's a mammal thing. We have big, strong jaw muscles. We actually have a hole behind our eyes. It kind of merges with our eyes, but you can feel the border when you feel your cheeks here. And that hole anchors jaw muscles. That's a mammal thing. And there are so many other features that make mammals mammals that we have that other mammals have. In the world today, there are three major types of mammals. We are placental mammals. And about 95% of all mammals are placental mammals like us. Placentals are the ones that can give live birth to well-developed babies that can develop for a long time in their mother's wombs. So dogs and cats and bats and whales and elephants, all placental mammals like us. But there are two other groups. One of those groups is the monotremes. These are mammals that still lay eggs. They are very primitive mammals. And these are the platypus and the echidna species of mostly Australia. So in looking at them, it's not that the ancestors of mammals would have looked exactly like them. They're specialized in their own way. But in looking at them, we get a glimpse of this time when mammals still laid eggs. The third group are the marsupials, and these are ones that are very common in South America and in Australia. There is one that's common in North America, the possum, that's made its way back up quite recently. But these are the mammals that give birth to tiny little babies that are born very premature, that then develop more further in their mother's pouch. So these are the three major types of mammals. Placental mammals are the dominant ones today, but we see the roots of these three major groups back in the Cretaceous period. Now, what we see in the fossil record is that those features didn't just evolve in one burst. They evolved one by one over time in many ancestors. Things like hair, for instance, goes way back, even before true mammals, to some of our antecedents living in the Permian period and in the early part of the Triassic period. But where we see a lot of change is right around the origin of true mammals. The very first true mammals were around late in the Triassic period and then early in the Jurassic period. And we see the first fossils of true dinosaurs about 230 million years ago, the first fossils of true mammals or their closest relatives around the same time. But if we look from the Triassic onwards, from that moment that the first mammals and dinosaurs entered the scene, dinosaurs and mammals would be living together for a long time, but they had different fates. Dinosaurs were destined for greatness, for grandeur. Some dinosaurs became massive, the biggest animals ever to live on land. Whereas mammals, they went the opposite direction. They went small, and they stayed small for a long time. No mammal that we know of was bigger than a house cat. And as they got smaller, their brains got bigger, their jaws simplified, their teeth changed from the teeth of their ancestors, where you would have just new teeth growing all the time, kind of like in a shark today. And this changed. They were drinking milk. They had one set of baby teeth, one set of adult teeth. Some of the bones that used to be in their lower jaw shriveled up and actually moved into the ear to amplify hearing. This is a classic mammal thing. And all these things were happening as mammals were getting smaller and smaller. It seems like miniaturizing their bodies drove a lot of these adaptations in the very first mammals. And there is this stereotype, this misconception that the mammals living with the dinosaurs were all just these small, boring, general little afterthoughts of Earth history. No, that's not the case at all. And with fossils, we see this. Now, for a long time, there were not a lot of good fossils of the mammals of the Triassic, Jurassic, and Cretaceous living with dinosaurs. These were small animals, it's true. And because they were small, it was hard to turn them into fossils. So for a long time, it was only a few little jawbones, a bunch of isolated teeth, and that's all that we really knew. We had to reconstruct a whole story based on meager fossils. But more recently, especially in northeastern China, in these same ecosystems buried by volcanoes where you get feather-covered dinosaurs preserved, you also get a lot of fossils of the delicate skeletons of little mammals covered in hair. And these fossils tell us quite bluntly that yes, mammals were small. The mammals living with dinosaurs were small. There's no way around it. There were no woolly mammoths or saber-toothed tigers or whales or anything like that back then. That's true. But just because mammals were small, it doesn't mean they were boring. It doesn't mean they were all generalized. It doesn't mean they were unimportant. Quite the opposite. There was a great diversity of small mammals. There were mammals that could burrow, mammals that could climb and clamber, mammals that could run pretty fast, mammals that could swim, mammals that had wings of skin that they used to glide between the treetops, all living with dinosaurs. So really, mammals were the kings and queens of the underworld. They were the small ones living in the understory, coming out at night, living underground, in a world that dinosaurs, at least on the surface, seem to dominate. And what's really intriguing to me is that mammals and dinosaurs reached an equilibrium. They kept each other in check for 150 million years or so. Yes, dinosaurs kept the mammals small. Being small, the size of mice, the size of rats, that is what mammals needed to be able to survive in a dinosaur-dominated world. But conversely, the mammals kept the dinosaurs big. And what I mean by that is we never find a fossil of a T-Rex the size of a mouse, a Triceratops the size of a shrew. Mammals were the ones that were being very good at being small. Now, during the Cretaceous period, there was this burst of evolution, not just of mammals, but of lots of other species, that we call the Cretaceous Terrestrial Revolution. It's a bit of a bombastic term, maybe, but in many ways it was revolutionary because it touched so many aspects of life and of food webs and of ecosystems. And what really triggered it, it seems, was the rise of flowers. So in the world today, flowers are all around us. So much of the food we eat comes from plants that have flowers. Even things like wheat and corn, those are grasses. Grasses are a type of flowering plant. The plants in our gardens, the plants in our parks, most of them have fruits and flowers, and they have beautiful fragrant smells. A huge percentage of the plants today are flowering plants, but flowering plants are a very new innovation in the history of life. The oldest fossils of plants with flowers are from the Cretaceous. So for the first, 4 billion plus years of Earth history, no plants with flowers. Now, when flowering plants entered the scene, they diversified, they adapted. Some of them became big, became trees. We have palm and magnolia trees in the Cretaceous period. As they did so, as they diversified, that triggered the diversification of insects, the insects that pollinated those flowers, insects that would eat those plants. And that, in turn, promoted the diversification of other animals, too, animals that would eat the insects, and then also, of course, animals that would eat the leaves and the flowers and the fruits and the roots of these flowering plants. So that humble, what seems like a very humble origin of a flower, it triggered something groundbreaking and something revolutionary. And mammals in particular really blossomed during the Cretaceous Terrestrial Revolution. And a lot of the modern groups of mammals, it's not that they quite got their start then, but their immediate ancestors got their start during the Cretaceous Terrestrial Revolution. And one of the key things is that there were all these mammals that were eating bugs, that were eating fruits and eating flowers. And that is involved in the evolution of a new type of tooth, a new type of molar tooth, the type of molar teeth that we have that can both shear food and crush food. These are very distinctive teeth, very intricate teeth. You look at a tooth of a shark or a crocodile or a T-Rex, yeah, they might be plenty scary looking, but they're pretty simple, steak knives. But our teeth, no. All the ridges, the valleys, the depressions, the way they interlock with each other, that's the classic mammal molar, and that evolved during this time of the Cretaceous Terrestrial Revolution as all these new food sources, insects and flowers and fruits and so on, were there to be enjoyed. Mammals had to survive and endure and persist for a long time in a dinosaur-dominated world. I mean, a single footstep of a brontosaurus could probably obliterate a whole colony of mammals. So mammals had to learn how to live incognito. But it also set them up to take advantage of one of the luckiest breaks in Earth history, at least from their standpoint, and that is when the asteroid hit. Not a lucky break for the dinosaurs, but all of a sudden the world is thrown into turmoil. And these dinosaurs that for so long were accustomed to being at the top of the food chain, to being the dominant animals, now they were on their back feet. They were at risk. They were vulnerable. They were so big, they needed to eat so much food. They couldn't hide very well, and they succumbed when the asteroid hit. But mammals had fine-tuned their survival abilities. They had honed their adaptations over 150 million years of living underfoot of the dinosaurs. And that adaptability, that resiliency, that really allowed them to stare down that asteroid. During the first 10 million years or so of evolution after the asteroid, there were mammals. There were lots of new mammals. These mammals were getting bigger. It was mostly placental mammals, the ones that could give birth to bigger babies that were part of this evolutionary spasm that was happening. And that's probably not a coincidence. Being able to give birth to larger, more developed babies could help them achieve larger sizes overall. But there's a really interesting story that we've pieced together recently. This is research that's come out of my lab at the University of Edinburgh. It's been largely led by Ornella Bertrand, who is a postdoc scholar with me and is now a young professor in Spain. And this is a story that really strikes at the heart of what we think of when we think of mammals. It knocks us down a peg a little bit. And so I'll explain, because I didn't expect this to be the story, but it turns out to be true. Very early mammals living with dinosaurs did evolve pretty sizable brains for the small little animals that they were. And that might have allowed them, our mammal ancestors, to survive, at least in part. It may have been part of the story for why they could survive the asteroid. They were pretty smart. But that is when evolution goes off on a weird path. Because you might think that, okay, modern mammals are really smart, and mammals survived the asteroid, and mammals diversified so much right after the asteroid to replace the dinosaurs. So maybe it was being smart and evolving bigger brains that helped mammals take over the world when the dinosaurs died. But that turns out not to be the case, because we have CAT scanned all of these skulls of fossil mammals. We have built digital models of their brains. We can measure the size and the shape of their brains. We can plot it out on the family tree of mammals, and the picture is quite clear that during the first 10 million years or so after the asteroid, the mammal brains actually got smaller relative to their bodies. So to put it very glibly, mammals were actually getting a bit dumber during the time after the asteroid. Now, I know intelligence is about a lot more than just brain to body size, but to be very glib about it, mammals were decreasing the size of their brain relative to their body. So what was going on? Well, it seems like what's really underwriting all of that is that the bodies of these mammals were getting so huge. So the asteroid wipes away T-Rex and Triceratops. The classic dinosaurs are gone. Some mammals have survived. These mammals have never gotten bigger than cat size for 150 million years. Now their dinosaur overlords are gone. Those jobs at the top of the food chain, the top meat eaters, the top plant eaters, they're suddenly available. So what do mammals do? They get big, and they get big fast. And in New Mexico, where I've done a lot of field work, where we have some of the best fossils of early mammals living right after the asteroid, we see that within 200,000 years of the asteroid, there are now mammals the size of pigs. Remember, they never got bigger than cats for 150 million years. Now they're the size of pigs. Within 1 million years, mammals the size of cows. So mammals are ballooning their bodies in size, and their brains are lagging behind. So the real evolutionary force is mammals are really going into overdrive, evolutionary overdrive, to get bigger, fill the dinosaur niches. And it was not intelligence that was driving things then. But intelligence did catch up. And by about 10 million years after the asteroid, that's when we start to see mammal brains now getting bigger and bigger and bigger. And it's from that burst of brain size evolution that these super huge brains of modern mammals, especially of us, it's from that burst of evolution that these brains emerged. But during this first 10 million years of the age of mammals, it wasn't the modern types of mammals that we all know that were the ones that were really in charge. It was their ancestors. It was this whole host of archaic placental mammals. Things like pantodonts and taniodons and tylodons and condylarths, these mammals, names that mean nothing unless you're a paleontologist, that were thriving. They eventually would go extinct, but in doing so, they would spin out the ancestors of the modern groups that we all know, including our own group, the primates. It was about 10 million years after the extinction. So we're talking about 55, 56 million years ago, as the Paleocene interval turned into the Eocene interval of time. That's when the modern mammals really start to make their presence known. And this happens at a time when the Earth is undergoing this moment of harsh, sudden climate change. Global warming, the most recent big global warming spike in Earth history before today. And it was caused by volcanoes. That's what often caused global warming during the long span of Earth history. In fact, it's the volcanoes that still erupt in Iceland today that started to erupt back then. They were much more powerful back then. There was a lot more lava back then. And all that lava burning through the Earth as the North Atlantic Ocean opens up, lava that actually scoured a whole lot of Scotland. Even the field sites. I have sites on the Isle of Skye where there are Jurassic Age dinosaurs, and we have the lava flows right over those dinosaur bones. That is causing global warming. And paradoxically, it didn't cause a big mass extinction this time. That actually gives me some hope for the modern world, that just because temperatures rise doesn't necessarily mean you're going to have a huge extinction. It doesn't mean it's good, because as we see from the Paleocene transition, maybe there wasn't an extinction, but there was a period of upheaval, a period of change. And what happened was, it seems like it triggered this mass migration of mammals. Now a whole lot of the world could be traversed. The high latitudes, they were free of ice. It was easy to move around. So mammals were on the move, and that unsettled things. And from there, this new reality emerged where modern primates, rodents, hoofed mammals, they become dominant at that time. And a lot of these more archaic mammals, these ancestors, they sputter away to extinction. And since that time, it has been those mammals, primates, rodents, hoofed mammals like cattle or horses or rhinos, and then later on, bats and whales and so on. It's those mammals that are the preeminent ones today. And it's largely because of that spasm of climate change that helped them take over the world. Mammals move. Many animals move. That's really the story of Earth history, but we really see it with mammals. But there's a difficulty there, at least compared to dinosaurs. When dinosaurs got their start, and during the first many tens of millions of years of the history of dinosaurs, all the land was gathered together. It was Pangea. They could move quite easily. But for more modern-style mammals, it's harder to move around. We have all these separated continents, and that's been true for many tens of millions of years. But some mammals have found a way, against the odds, to move vast distances across those continents. And they've done so, in some cases, by flying. Bats enter the fossil record about 55 or 56 million years ago as temperatures increase. And they evolved wings and they could fly, and that really was a ticket to global success. They could move all around. But for mammals that couldn't fly or couldn't swim long distances, there was another way that every once in a while, by sheer chance, they could move around quite long distances. And that is by what we call these Hail Mary dispersals. So if you're an American football fan, you know sometimes your team is down and you have one last chance and you just throw the ball down the field and hope that your receiver catches the ball, scores a touchdown. The odds of success are very low because the pass is so long, but every once in a while that pass connects and your team wins the game. We see this with migrations. There are mammals in South America today, both primates and rodents. So the classic monkeys, the howler monkeys of South America, and some of the classic rodents of South America, guinea pigs, capybaras. They've been there for a long time. How did they get there? Nobody really knew. South America was an island continent for many tens of millions of years. How did these mammals make their way? They couldn't fly. They couldn't swim. They couldn't jump between land bridges. How in the world could they get there? Well, the answer started to become really clear with the genetics of those mammals. It is clear from doing the DNA paternity test that they are closely related to African rodents and primates. Okay, so how do African rodents and primates get to South America? Well, it seems like the only way is through one of these Hail Mary dispersals, where there are some of these mammals, maybe after a storm, maybe they're on a raft of vegetation, sometimes big chunks of the coast, trees and grass and all kinds of stuff can be ripped apart, thrust out into the ocean, and can actually travel the currents for many weeks and then land somewhere on a distant land. And that seems to be how the rodents and the primates got to South America. And it seems inconceivable. How in the world could they survive a voyage like that? But we have to remember that evolution has lots of time to work with. And if you're talking about many, many, many millions of years, most of the time there was some storm, some little bit of the coastline was ripped out, it would go out in the water, nothing would come of it. But maybe every once in a while there would be a Hail Mary play, and that raft of vegetation carrying these monkeys and these rodents would reach thousands of miles away, and they would have a new shoreline to colonize. And that is what happened. And I think it is one of the most incredible stories of evolution. We wouldn't know about it if we didn't have the genetics and the fossils together to tell us that story. After the asteroid hit, the Cretaceous turned into the Paleocene, the age of dinosaurs gave way to the age of mammals, but really, this greenhouse world of the dinosaurs persisted. The Earth was still very warm. There were no ice caps at the poles, for instance. Then the Earth got even warmer as the Paleocene turned into the Eocene with this spurt of global warming. It got so hot that there were crocodiles lounging in the shade of palm trees above the Arctic Circle. And the Earth stayed hot for a while, but then it started to gradually get a little bit cooler. The tide shifted there. And about 35 million years ago or so, it really started to get cooler. And what happened was there were different changes in the orbit of the Earth and the amount of carbon dioxide in the atmosphere, small things that over time can add up and create quite profound climate change. But what really drove this, what turned a small cooling trend into a big trend of decreasing temperatures, was that Antarctica became isolated. Antarctica was connected to South America ever so tenuously by a little tendril of land. And that was snipped, just tectonically, just the way the Earth's plates move. And now suddenly, you could have cold water currents encircling Antarctica at the bottom of the world. And this acted as a global air conditioner. And ice nucleated onto Antarctica. The glaciers grew into ice sheets. And that helped drive the temperature of the entire world to be much cooler. Now, this was a long-term trend then that continued to happen for many tens of millions of years. About 2.5 million years ago, another interval of change happened. There was a switch that was flipped again, and this had to do with how changes in the orbit of the Earth, the shape of the orbit of the Earth around the sun, how circular it is compared to how oval, there's small changes, the tilt of the Earth's axis, these things that may seem subtle, these things actually, just by chance, converge together to make the Earth receive less light and energy from the sun. Added on to this global air conditioner of the ocean currents changing, that now plunged the Earth into a proper ice age. And this is the ice age, the one that we all think of when we hear the word, when we see the movies. This is the time of woolly mammoths and saber-toothed tigers. It only started about 2.5 million years ago. And in fact, we're still in that ice age. It's just we are heating the Earth so quickly through global warming that we're basically burning ourselves out of the ice age. But over the last 2.5 million years, the Earth has been cold. Now, it's not that the entire Earth has been covered in glaciers. No. What's happened is those polar ice sheets have grown to such size that at certain times they have crept down onto the continents. This is especially true of the North Pole ice sheet. It's grown, it's contracted, expanded, contracted. In many pulses, it's like a roller coaster, just as small changes in the orbit of the Earth occur. About 50,000 years or so was one of the peaks of the expansion of that ice sheet. And that ice sheet grew so big that it crept down and it covered Chicago, where I'm from. It covered Edinburgh in Scotland, where I live now. It covered New York City. A lot of North America, a lot of Asia, a lot of Europe was completely engulfed in ice. There would have been a mile thickness of ice covering New York City and Chicago 50,000 some years ago. Now, living on the fringes of the ice sheets were the woolly mammoths, the saber-toothed tigers. There were woolly rhinoceroses. There were armadillos the size of Volkswagens. There were sloths that lived on the ground that stood 10 feet high. They could dunk a basketball. There were giant deer with antlers bigger than a dinner table. There were American lions and hyenas. Incredible time of mammal diversity These mammals had to live and adapt to this cold world, and many of them did so by getting big, being big pays when it's cold, and by evolving these really shaggy coats of hair. Generally speaking, when it comes to the mammals that lived on land, some have gotten pretty big. There are big elephants that live today. There were even bigger elephants that lived in Earth history. There were huge rhinos without horns that lived many tens of millions of years ago that got up to be maybe around 15 to 20 tons. Pretty big, but nowhere near the size of the largest dinosaurs. Some of the long-necked dinosaurs, like Argentinosaurus and Patagotitan, these things were heavier than Boeing 737 airplanes. They weighed 50, 60 tons or even more. Absolutely gargantuan. And they pushed the boundaries of what's possible in biology. I mean, it's incredible. They would have hatched from eggs that you could hold in your hand, and they would have had to grow and endure all of the tribulations of life to reach that size. No mammals have been able to do that to that degree. And it is a little bit of a mystery, but I think it's probably several things put together that may explain it. But one of the key reasons that I think that dinosaurs were able to get so much bigger than land mammals is that they breathed in a totally different way. Mammals like us, we know how we breathe. Our lungs are basically bags. They inflate, they deflate. We breathe in, we breathe out. But birds today have a very different type of lung. The lung of a bird is not like a bag that inflates and deflates. No, it's more like a set of pipes or a set of straws. And air can only go through in one direction. And the whole way that birds make it work is that they attach these air sacs, these balloons that can store air, they attach them to those lungs. That controls this unidirectional airflow. What that also means is that birds can get oxygen when they breathe in and when they breathe out, just because some of that oxygen-rich air is shunted off to those air sacs, and then when they deflate, that air moves across the lung, there's still oxygen there. It doesn't, and it's fine if you don't understand. It's a feat of engineering. I think you really have to be an engineer to understand how it works. But what it means is that birds have much more efficient lungs than mammals. There are birds that can fly over the Himalayas. We, a mammal, if we're in an airplane and the cabin depressurizes at that sort of altitude, we got to get the oxygen masks. That's because our lungs are less efficient. The key thing here is that we know many dinosaurs had those same lungs as birds. T-Rex did. The long-necked dinosaurs did. How do we know it? Not because the lungs fossilize, because lungs are flimsy, they decay very quickly, but those air sacs that stick out from the lungs, they actually invade the bones in a very characteristic way. They enter holes in the side of the bones, and they open up inside of the bones into these big chambers. And we see that, the exact same structures in birds today, in T-Rex and the long-necked dinosaurs. So to circle back here, we know that a lot of these dinosaurs, including the very biggest dinosaurs that ever lived, had these ultra-efficient lungs. They could take in more oxygen than any mammal. And that's probably a major reason why these long-necked dinosaurs were able to get bigger than the biggest elephant, the biggest rhino, the biggest land-living mammal ever. Some of the most remarkable mammals of all, to me, are the whales. These are mammals, okay? They look like fish. They really do. I mean, and they swim at incredible depths. They never come onto land. They are fully aquatic animals, but they are mammals. And they have the classic features of mammals. We know they're mammals. They even have hair. A lot of them have whiskers and eyelashes and so on. They feed their babies milk, all the classic mammal stuff. Their DNA proves that they are mammals. When we do the DNA paternity test, whales actually slot right into the mammal family tree, and it's hippos that are their closest modern relatives. So they are hoofed mammals, just very derived, very modified hoof mammals that underwent this incredible evolutionary transformation. They transformed their bodies from a land mammal to an ocean mammal. How do we know that part of the story? Well, we actually have fossils that show those different transitional stages. Now, we don't have fossils of every stage, but we have enough fossils we can string them together into a sequence, and kind of like a flip book, you have these different stages, and if you look at them in a running film, you get that story of how a land mammal turned into a whale. And the starting point of that story is somewhere around 55 million years ago. The Eocene interval of time is dawning with this burst of global warming. There are small hoofed mammals that are living in different parts of the world. In what's now India and Pakistan, there were these tiny little creatures. They looked like little deer, fast runners with hooves that lived on the land, but they had a few interesting features of their skeletons, including denser bones, that would have allowed them to spend some time around the water, similar to hippos today. And then we see, stage by stage, how the hooves of these animals start to change. They start to morph into flippers. At first, flippers that can be used on land and in the water. But then the fore flippers get really big. The hind ones shrink in size. The bodies change. They get longer, more tubular shaped, like a torpedo. And by this point, these whales, they couldn't have come back on land anymore. They were fully ocean-living species. It is an incredible story of evolution. It is a textbook example of a major evolutionary transition, how one type of animal with a body that is suited for living in one type of environment changes itself thoroughly to live in a totally new lifestyle. Because I consult on the Jurassic World films, people are always asking me if it's possible that we could bring dinosaurs back to life, if we could find dinosaur DNA and clone a T-Rex and have a T-Rex in the world with us today. And I always have to tell people, for better or for worse, it's very unlikely. You never say never, right? As a scientist, you never want to say something's impossible, but nobody's found any DNA that's older than about 1.5 million years or so, at least as far as complete good DNA in the fossil record, because DNA breaks down really quickly when an animal dies. So it is unlikely a T-Rex we could ever bring it back to life, which for me is fine. I don't want to deal with the T-Rex. I'm happy studying its bones. But for things like woolly mammoths and saber-toothed tigers, they lived much more recently. They went extinct really just a few thousand years ago. We have their DNA. We know the complete genome of the woolly mammoth. We know more about the DNA of woolly mammoths than we do about a lot of animals living today. We have fossil specimens of woolly mammoths that have been frozen in the ice, and they have hair, and they have the organs and the muscles, they have last meals in the stomachs. These animals are so much closer in time to us that maybe they could be brought back. Now, I'm not a geneticist, and I won't pretend to understand what it will actually take to clone a mammoth or a saber-toothed tiger. I'm sure it is not easy, and I don't want to trivialize what is certainly very hardcore science. But what I think I have a little bit more perspective on is just the deep time history of the Earth. And what I would say is that there is a real risk of bringing back extinct species because the world today is a lot different than the world that they knew. That's definitely true of a T-Rex. But even a woolly mammoth, these were animals that were adapted to the Ice Age. The world was a lot colder then. Their habitats have mostly disappeared. They would be living in many ways on an alien planet. So the ethics of that get very tricky. On the flip side, the whole reason the woolly mammoth doesn't live anymore is really because of us, because of humans changing the environment so quickly, so thoroughly. Overhunting, but not just overhunting woolly mammoths, but changing the land, clearing vegetation. This is why woolly mammoths and a lot of the other megafauna went extinct. It wasn't because of an asteroid. It wasn't because of volcanoes. It was because of us. So can we rectify things? Can we have penance for our sins as a species by bringing a woolly mammoth back? That's part of the ethical equation as well. It's a tough, deep question. And I'm not going to give an answer because I don't actually have an answer. I think different things about this conundrum all the time. But I do think, from what I understand of genetics, what I know about what's happening with science, that it might be possible. It might be possible. So this is not some pie-in-the-sky thing that we can debate philosophically, at a coffee shop. Should we do it? Could we do it? No, this might be a real-world thing that we have to deal with. So I think we need to be prepared for having this debate about whether it is ethical to bring back recently extinct species.
Chapter 4: How Birds Became the Last Dinosaurs.
Birds, the birds around us today, they are dinosaurs. They are real, true dinosaurs. And that's not just a turn of phrase. That's not just some technicality. Birds are dinosaurs because they are part of the dinosaur family tree. They evolved from other dinosaurs. They are just a strange type of dinosaur that got small, evolved wings, and developed the ability to fly. And in that way, really, they're a dinosaur version of a bat. A bat is just a strange mammal that got small, evolved wings, and developed the ability to fly. But of course, it is still a mammal. And in that sense, birds are still dinosaurs. They're just the only dinosaurs that have lived on to the modern day. And this idea is so enthralling to me that it's inspired me to write my newest book, which is called The Story of Birds. And that book tells the story of how birds evolved from dinosaurs, how dinosaurs evolved feathers and wings and took to the skies, and then all the amazing things that birds have done in the 150 million years since they entered the scene. In writing The Story of Birds, I learned a lot, and I gained an incredible appreciation for birds. But the birds today, even the really scariest ones today, and I'm not talking about robins, I'm talking about the properly scary ones, say hawks and eagles and vultures and so on, they pale in comparison to some of the extreme, eccentric, extinct birds that once lived. And I'm talking about things like terror birds. Okay, I think the name says it all, but the nickname is well-deserved. These were the top predators on South America for tens of millions of years after the asteroid. They became bigger than humans. They had heads bigger than a horse's head, with a big, nasty, hooked beak at the end that they used for devouring prey. They were ferocious. They could run fast. They had big, powerful legs for kickboxing their prey. There were things called demon ducks that lived on Australia for tens of millions of years. Now, this nickname is a little bit unfair. It's a little bit of a misnomer because they wouldn't have been very demonic. They were big. They were like 100 times the size of a modern duck, but they were plant eaters. And they were, in fact, some of the most important big plant eaters at the base of the food chain in Australia, along with some marsupials like kangaroos and wallabies and so on, for many tens of millions of years. Our human ancestors, and actually not even our ancestors, our species, Homo sapiens, when they first reached Australia, met the demon ducks, ate demon duck eggs for breakfast. There are archaeological sites where there are charred demon duck eggs, sadly, probably why they went extinct. But they were some of the heaviest birds of all time. Joined with another group, there's like a joint heavyweight title with these things called elephant birds from Madagascar that stood like 10 feet tall, that weighed like 700 or more pounds. Actually, some of them may have even pushed close to a ton, weighed more than cows. They laid eggs the size of watermelons. There were things that were called colossus penguins. These were penguins that were taller than a human and weighed as much as a gorilla. They were the top predators in the southern oceans after the ocean reptiles went extinct with the dinosaurs at the end of the Cretaceous. Later on, they were superseded by killer whales and big sharks, but for many, many millions of years, it was gigantic penguins that were the big fish eaters and flesh eaters of the oceans. And there were some giant birds. A lot of these, by the way, I should say, the big penguins, the terror birds, the elephant birds, the demon ducks, they could not fly in the air. They gave up flight in order to get so big. But there was one group that got big, but maintained the ability to fly, and these were what we call the pelagornithids. They don't have a catchy nickname yet. Somebody needs to come up with one. Let me know if any of you have any good ideas. But these had 20-foot wingspans. They were like kites, giant kites that soared the thermals around the world for many tens of millions of years, giant hang gliders. And I could go on and on and on, but the point really is that the birds we see today, as diverse, as remarkable as they are, really, it's just, they pale in comparison to a lot of the birds that once lived that are now extinct. Now, this idea that birds are dinosaurs, that birds evolved from dinosaurs, you might think that it is a brazen, audacious new idea proposed by the new generation of paleontologists. But no, and it's not. In fact, it's a very old idea. And it goes back to the time of Charles Darwin. It was in the 1860s, right as Darwin was releasing The Origin of Species, articulating his ideas for evolution by natural selection. It was then that some of Darwin's closest scientist friends made the connection between dinosaurs and birds. And it was Darwin's dear friend, Thomas Henry Huxley, Darwin's bulldog. That's what they called him because he was so voracious in the way that he advocated for Darwin's ideas. Huxley was a great communicator of science. This was a day, in a time before there were a lot of pop science books, but people communicated science quite broadly through lectures. And this is what Huxley did. And very famously, in the 1860s, in a series of lectures, beginning in London, Huxley proposed this idea that birds evolved from dinosaurs. And this was in service of more broadly communicating to the public that Darwin's ideas about evolution were true. What Huxley understood is that, yes, today's birds are very distinctive, with their feathers, their wings, their wishbones, their beaks, their lightweight skeletons, their stubby tails, their fast growth, their high-powered metabolism, of course, their ability to fly. These are very unique things. And there's really nothing else today that looks like a bird. But if you look into the fossil record, you can actually see that there are more primitive creatures that lived long ago that have many bird-like features. And these are dinosaurs. This was around the time in the 1860s that some of the very first good skeletons of dinosaurs were being found, and Huxley noted the similarities. And they were things as basic as, look at the foot of a chicken, and it really looks like the foot of a small meat-eating dinosaur with the 3 toes and the claws and so on. This was before anybody even knew what DNA was, so it was all based on similarities in the fossils. And what really clinched the deal for Huxley was when this new fossil was discovered in the early 1860s in southern Germany from rocks that dated back to the Jurassic period, about 150 million years ago. This was the fossil of a bird. It had wings, it had feathers. Of course it was a bird. What else could it be? But it was no normal bird. It was a weird bird. It still had teeth in its jaws, little steak knife teeth that looked like the teeth of a little dinosaur. It had big claws on its hands, like the claws of a little dinosaur. It had a long, bony tail. It really looked like it was half bird, half dinosaur. Now, this is Archaeopteryx. It remains a famous fossil. It remains the oldest known true bird, an animal with feathers and wings that could fly. And in it, Huxley saw this perfect intermediate stage, this Frankenstein creature. And this was the argument that he made to the masses. And by the end of the 1860s, actually, people, at least in Britain, were convinced largely that birds came from dinosaurs. Darwin put it into his latest editions of The Origin of Species. It became a widely known idea. But then, as often happens in science, when an idea starts to reach consensus, it started to attract its contrarians. And people started to find new dinosaurs, giant dinosaurs, as the American West opened up. Allosaurus and Brontosaurus and Stegosaurus. These things look nothing like birds. So how in the world could a bird come from dinosaurs like these? That's what people started to argue. And it took many decades for the debate to circle back around through the discovery of some really bird-like raptor dinosaurs like Velociraptor and Deinonychus that brought it back and that showed that Huxley was actually right. And then in the 90s, finally people discovered feathers on dinosaur fossils, and that was it, the final piece of evidence to prove once and for all that yes, today's birds really did evolve from dinosaurs. In the world today, you look around, there are so many birds that we are familiar with. There are more than 10,000 species of birds, and we see them around us. Many of us go bird watching. Some of us have pet birds. Some of us enjoy chicken for dinner. There are so many birds. All of that diversity stems from dinosaurs. And it's not like there were 10,000 different dinosaurs that gave rise to the different species of birds today. No, what happened was that there was basically one great-great-great-great-great-great-great-grandmother dinosaur that evolved the ability to fly, and from that ancestor sprang all of the diversity of modern birds today. But that ancestor and the descendants of that ancestor had to traverse and endure so many tribulations. They had to do the same thing our mammal ancestors did, and that is survive the asteroid that ended the Cretaceous and killed 75% of all species, including every other type of dinosaur. And it really is a remarkable story because imagine, if you will, an alternative world where every type of mammal, including us, goes extinct and only bats survive. That's basically what happened to the dinosaurs. So how do they do it? We can say, well, birds, okay, they could fly, so that could help them get away from danger very quickly. Birds are generally small. They could hide away more easily than a T-Rex or a Triceratops. Those things probably help them, and that is certainly true. But the real crux of the issue, the real mystery is, why did only one type of bird survive? Because when the asteroid hit, there was a whole panoply of birds. There were very derived, advanced modern birds with beaks that grew really fast and could fly really well, but there were still birds with teeth and long tails and claws on their hands. So why did only modern birds survive? Why did they not follow T-Rex and Triceratops to the grave? And it seems like it is probably because simply the Earth devolved into this fickle casino. There was no time for species to adapt through the longer-term processes of natural selection. You had to face the asteroid and the tsunamis and the fires and the earthquakes and the nuclear winter. You had to face that with whatever hand of cards you were already dealt. And modern-style birds not only could fly, not only were they small, but they grew super fast and reproduced really quickly. That would help. The generations could turn over quickly. And they had beaks. These were some of the birds that had beaks, and those beaks were very good at eating seeds. And that might sound trivial, but today, when there's a forest fire, when a volcano obliterates an island, plants will grow back. And why is that? Because seeds can last a long time. If you were an animal at the end of the Cretaceous and you ate parts of a growing plant, leaves, flowers, fruits, roots, your food would have run out really quickly. But if you could eat seeds, that would be your ticket for surviving longer. That would be like the last food source available. So having beaks, eating seeds, in addition to being small and flying well and growing fast, was probably the winning hand of cards at this crazy, maniacal poker table at the end of the Cretaceous. And I think it is a really, in many ways, quite haunting image, but also an image of resiliency to think about in those weeks and months and maybe years after the asteroid. So many animals died, but there were these modern-style birds like Asteriornis, which is known from Europe, Vagavus from Antarctica, these birds that would have been using their beaks to pick through the wreckage, spearing seeds amidst all the fungal spores and the glass bullets from the asteroid and the charcoal from the wildfires. And something that seems so trivial, so basic, just so happened to be their get-out-of-jail-free card. And that, in large part, is what allowed birds to survive to the modern day. When we look at birds today, they are utterly unique and distinctive. There are no other animals that really look anything like birds, especially when it comes to feathers and those sort of aspects that are distinctly avian. But more broadly, there are so many parts of the bird body that work together to enable that most birdie of things, and that is to fly in an active way by flapping the wings, powered flight. And you think of wings and feathers, but you also think of a light skeleton, bones filled with air, a wishbone that acts as a spring as the wings beat, a short tail with a big fan of feathers that's used as a rudder and for steering and for landing. There are so many things that if you take any one of those features away from a bird, it couldn't fly or it couldn't fly very well. So you might think that these things all evolved for flying so that birds could fly. But no, what we see in the fossil record is that these classic features of birds are actually dinosaur features. Almost all of them first evolved in the dinosaur ancestors of birds. They evolved long before birds or these dinosaur ancestors could fly. They must have evolved for reasons other than flying. And the story of a bird evolving is really a story of gradual piecemeal evolution. Tens of millions of years of different features evolving one by one in different dinosaur ancestors for different reasons but then coming together eventually, really through chance, to form what could function as a flying machine. And I think the best analogy for that is that the Wright brothers invented the airplane. We all know that story. But they didn't invent all the components of the airplane. They didn't invent the wheel. They didn't invent the propeller. They didn't invent the wing. Other people had invented those things, many thousands of years before in some cases, for different reasons. But the Wright brothers put them together in a way that could fly. We can talk about a few of the different classic features of birds and actually see how they first evolved in dinosaurs. One of them is walking bipedally. That's just the fancy way of saying just walking on the hind legs. This is what we do, so we kind of take it for granted, but really it's quite unusual in nature. And there's this famous line from the ancient Greeks that humans, how do you define humans? Well, they are featherless bipeds. So really what that means is just that the other animals alive today that walk on their hind legs are birds. Now you might think, okay, birds need to walk on their hind legs. They have their wings, they use their wings to fly, they use their legs to land and to take off and to move on the ground. But no, actually being bipedal long predates flying. Early dinosaurs became bipedal. Some of the first dinosaurs living on Pangaea back in the Triassic period started walking only on their hind legs. Probably in order to move faster, to run faster, to move more efficiently, to free their hands for doing different things, for grabbing food, and so on. So it had nothing to do with flying. Feathers. Feathers. Nothing is more birdy than feathers. You find a feather, you see one fluttering around in the breeze, you know a bird was there. No lizard, no snake, no turtle, no mammal, no fish has feathers. They are uniquely bird features. But when we look at the fossil record, we see that a lot of dinosaurs had feathers. We actually see that feathers were normal for dinosaurs. We have dozens of different types of dinosaurs that have been found with feathers all over their bodies. Small dinosaurs the size of dogs, big dinosaurs. There's a tyrannosaur that's more than 30 feet long and weighed more than a ton. It had feathers all over its body. We see plant-eating dinosaurs with feathers and meat-eating dinosaurs with feathers. If you map this onto the family tree of dinosaurs, really the only conclusion is that feathers must go deep into dinosaur history. Probably the common ancestor of all dinosaurs, maybe even a more distant ancestor, first evolved feathers. But what we see from the fossils is that most of these feathers were quite simple. They were the starting stages, the beginnings of bird feathers. Most of these feathers were just little strands that looked like hair. They were hollow inside. They were made of these beta proteins that feathers today are made of, so we know they are feathers, but they're a simpler form of feathers. That's what most dinosaurs had. And those kind of feathers were normal for dinosaurs in the same way that hair is normal for mammals. And I think it goes without saying, but I'll say it anyway. We cannot fly with our hair. Okay, some of us have more hair than others, but if you have the most luxurious mane of hair, you can't fly with it. So these dinosaurs that had these hairy feathers, they could not fly with them. That means feathers must have evolved for something else initially. And we think it was for the same reason hair evolved in mammals, to help control body temperature, to stay warm, part of the metabolism, part of becoming more active and energetic and warm-blooded. Most dinosaurs had those simple feathers, but some dinosaurs elaborated those feathers, and these were the raptor dinosaurs. And as their bodies were getting smaller over time, they packed those feathers ever more densely all over themselves. And they started to line up some of those feathers on their arms, sometimes on their legs and on their tails. And those feathers changed from simple little hairs into brushes. So they branched out. And some of them became rigid but pliable and became the classic quill pen feather that we know today, the classic feather of birds. And some of these dinosaurs even had wings on their arms and sometimes their legs and their tails made of these feathers. And they look just like the wings of birds today. But again, the fossils throw a curveball because wings show up on dinosaurs that are about the size of sheep up to the size of horses. That's where wings first evolve. And those wings are no bigger than a laptop screen. So just by the laws of physics, there's no way that if that dinosaur flapped those wings that it could get aloft, that it could get the lift and the thrust, those aerodynamic forces needed to stay in the air and move around the air. So that means that even wings must have evolved for another reason. And we don't know exactly, we weren't there to witness evolution, but we can tell from the fossil melanin, the fossil color pigments in some of these dinosaur feathers, that they had quite elaborate colors and patterns. So we think that some of these dinosaurs were using those wings for display, basically advertising billboards sticking off the arms to attract mates, to intimidate rivals. What a peacock does today, it's not flying with that tail. And that's probably why wings first evolved. And then wings later on were repurposed as airfoils for flying. And it probably happened quite by accident. But the key thing is that feathers and wings did not first evolve for flying. The fossils make that clear. They were repurposed. But how were they repurposed? And did this happen once or did this happen multiple times? The reality is we don't have a firm answer, and it's not because we don't have the fossils. It's because, in a way, we have too many fossils. We have so much evidence, it's hard to make a clear through line with this evidence. But by and large, what the evidence that we know now, what that tells me, is that flying probably evolved multiple times in dinosaurs. And that modern birds are just one of those experiments in flying, the one that's happened to reach the modern day. Now, what's the evidence for that? Well, the evidence for that is there's a whole bunch of dinosaurs with feathers, with wings, but they're very different types of wings. Some have wings only on their arms. Some have wings on their arms and their legs. Some have wings on their tails. Usually the wings are made of feathers, but there's this one type of dinosaur. It's called Ichi. It's from China. It had a wing made of skin, kind of like a bat. Now, it also had feathers on the rest of its body. These are such different configurations. I mean, it's like the difference between a jet airplane and a passenger jet, a fighter jet, a blimp, a hang glider, a space shuttle, a rocket ship. The vast differences seem to indicate that there were different experiments in flying. And probably what happened was you reached this point in dinosaur history where there was this zone on the family tree of dinosaurs where there were a bunch of small dinosaurs that had feathers, that had wings. They evolved these from ancestors for different reasons. But now they could experiment with different ways. And they were all kind of around that threshold where their wings were big enough compared to their bodies that just through the laws of physics, they could flutter about in the air a little bit. Modern birds would have come out of that, or the lineage leading to modern birds, which then really changes the question in a way to how did modern birds, how did that one particular type of flying dinosaur start to fly? And here I won't profess to have an answer. I don't think we know the answer. There are different theories. And some of those theories sound pretty good. But the issue is that we weren't around to see it. And I think the fossils that we have are compatible with different scenarios. Now, some of the different theories are, there's one that's called the ground-up theory. And this is the idea that you had these small dinosaurs that had evolved wings for different reasons, for display. And they started to move those wings, and those wings gave them some lift and some thrust as they were running, and they allowed them to defy gravity. Okay, that could have definitely happened. Now, there's an alternative theory that it happened the other way, from the trees down, that there were small dinosaurs with wings living up in the canopy, using those wings for displaying to mates and rivals, and then also sometimes for gliding, for parachuting. And then by moving those wings, by flapping them, they would get more control, and those wings, in a way, could be used to manipulate gravity. Those are two end members, but there's other theories in between, that maybe it's little baby dinosaurs as they're learning to move that flap their wings, and that got them a bit of lift and thrust. There's all sorts of ideas. And evolution by natural selection, it doesn't work with a plan in mind. There's no grand designer that 230 million years ago, when the first dinosaur entered the scene on Pangaea, that pushed some button and said, one day these dinosaurs will fly. No. Evolution through natural selection doesn't work with that kind of agency. It really just works to fit individuals and their populations to their own time and place. And if there's some small change that can help an individual live a bit longer, survive a bit better, reproduce a bit more, have more offspring. That sort of feature, that is an adaptation that can then cascade through the population and change over time, and that's how species change over time. So everything about birds evolving from dinosaurs evolved through that process, steady accumulation of features over time. Then after some of these dinosaurs started to fly, it's not just that evolution stopped. No. Evolution turned their bodies into more efficient flying machines. And two of the ways that happens with the tail and with the beak. So the tails of the dinosaur ancestors of birds are really long, straight, bony tails. They had feathers on them, but they were quite cumbersome. Birds today basically don't have a tail at all. They just have a little nubbin of bone. It's called the pygostyle. If you roast a chicken on your Thanksgiving turkey, you might see this little thing that's often called the parson's nose in really old cookbooks, because it's this really fatty, glandular mess of tissue surrounding this tiny little fused up remnant of a tail. So birds have that kind of tail because nowadays birds anchor a whole bunch of feathers, of big feathers, to that tail, that shortened tail, and they use those feathers to steer and to brake and as a rudder. They're very important in takeoff and landing. So they change that long dinosaur tail into a tail that's more controllable and can be used for aerodynamics. When it comes to the front of the body, to the snout, to the face, to the business end, birds today have beaks. It's one of those classic bird things. The first birds did not have beaks. The first birds had a bunch of small little razor-sharp steak knife teeth on their jaws that looked just like the teeth of a velociraptor. Archaeopteryx, the very oldest true bird fossil from the Jurassic, has those raptor dinosaur teeth. We see over time the teeth reduce and the teeth are replaced by a beak. And this seems to have happened not just once, but many times independently. And it might have had something to do with flying, at least in part. Losing teeth, having a beak may have saved a little bit of weight for flying. Being very lightweight is important. But really, it probably had more to do with diet, with what these animals were eating. Maybe with foods that they were now able to eat better because they were flying. Things like different types of insects, different types of seeds, things that they could access more easily in the forest now that they could fly. But by the end of this all, by the end of the Cretaceous period, the time of T-Rex, the time of Triceratops, there were a whole bunch of birds flying overhead of those dinosaurs. Some were still quite primitive. Some still had teeth and claws and long tails. Others looked a whole lot like birds today, with a beak, with a short stubby tail, with the fan of tail feathers. And that's where the world stood on that day that the asteroid came down. When we go out from the city, away from cars, away from sirens, away from the many sounds of modern life, and we just listen, so much of what we hear, the soundscape of nature, is birds. It's birds singing and tweeting and squawking. And you think about birds today like songbirds that sing songs that they learn from tutors. That it's like a teacher and a student, and they have this babbling phase where they learn like a toddler. I was writing this book, as my little boy was growing up, and the parallels there just blew my mind. Now, when did that evolve? That's a really interesting question because it gets at, would the Cretaceous world of T-Rex, let's say, what would that soundscape have been like? Would it have been like the modern world, or would it have been very different? Might it have just have been the trees rustling and the T-Rexes screaming and the bugs buzzing around? The movies certainly aren't right. They wouldn't be roaring like lions. That's a very big cat thing, enabled by the unique vocal cords and bones of the throat of big cats. So to me, these are the questions, especially when, I'm working on films and consulting on programs that we often think about. What would that world have been like? Sound doesn't fossilize. There's no Cretaceous cassette tape that we can find in the fossil record and plug in and hear what these things were sounding like. But sometimes we do get clues from the fossils themselves. And in some rare cases, the vocal organs do preserve. And there is a bird fossil from about 68, 69 million years ago from Antarctica. This bird is called Vagavis. It's a very modern style bird. It had a beak. It grew really fast. It had big wings. It was actually in the duck and chicken part of the bird family tree. So a very modern bird living roughly at the same time as T. rex. The bones are well preserved. And inside the chest cavity, right above where the lung would have been, where the chest connects to the throat, is this cartilage structure that looks just like the voice box of modern birds, the syrinx. So it must be a syrinx. Now, a syrinx is a uniquely bird thing. We don't have it. We vocalize in the larynx in our throat. We have the vocal cords. That's the way mammals do it, and actually lots of other animals vocalize in the throat too. But birds have this organ basically right on top of their lungs, and it is an incredible organ. It has some of the fastest twitching muscle in the animal kingdom. Both sides of it, in some species, can work separately. So it'd be like you can speak English and French at the same time. I mean, it just blows my mind that birds can do this. We know that organ was present in at least some birds living in the Cretaceous period. So by the end of the Cretaceous, you would have had some birds that could sound like the birds of today. But it is really just one clue. We need to learn so much more. There are birds today that can migrate incredible distances. There are the finches on the Galapagos that are still evolving. They are spinning out new species in front of our eyes. And then there are birds like crows and ravens and parrots, which have huge brains, some of the biggest brains relative to body size of any animals, more so even than many mammals. They are basically feathered apes. And we know it. When a parrot repeats words that we say more clearly sometimes than we can. Amazing. When a crow recognizes itself in a mirror. When a crow fashions its own tools. I mean, a lot of animals use tools. They might pick up a stick and use it to prod open a nest of bugs or something, or to scratch. A lot of animals use tools. Crows do something that really humans and maybe some other primates can do, and that is fashion their own tools. They take sticks and other things and actually make hooks out of them and use them to get food. These are incredible feats of intelligence. And these are seen in animals that are with us, that share the world with us today. And I don't think we appreciate it enough. I don't think I appreciated it enough before writing the book, but I've really come to love a lot of these birds. And it's also inspired a lot of my research as a scientist. My lab at the University of Edinburgh, a lot of my students and I, we're working now with a big team of zoologists and neurobiologists to study how cognition and intelligence have evolved over time, and to try to make links between the intelligence and behaviors of modern species, especially birds, with things like T. rexes and brontosauruses. How did a dinosaur sense its world? We're trying to get at questions like that. And it's all inspired by learning more about birds. When it comes down to it, for me, it is astounding to look at even the most common bird, even a bird that might annoy us, even a bird that we don't give much credit to. We might swear under our breath at the pigeon that's walking in front of us on the street. Those birds, though, they are dinosaurs. They are real, bona fide, unequivocal, absolute, 100% living dinosaurs. They evolved from dinosaurs. They are part of the dinosaur family tree. They have all the classic features of dinosaurs. They are the only dinosaur that has survived all the whims and catastrophes of Earth history and extinctions and volcanoes and asteroids to reach the world today. And more than anything, that's what I appreciate about birds. They are the only ones of my beloved dinosaurs, the animals that inspired me to become a scientist as a teenager. They're the only ones of the dinosaur family that have made it to the world today, and they give us an opportunity to watch, to experience, to appreciate actual, real dinosaurs.
Want to support the channel? Join the Big Think members community where you get access to videos early, ad-free.